Oh, yeah, sure.
Right. 大家好，我是 Business 主办人 Oscar， funding Sandra， 大家 Sandra， 第出来的人请举手。好，我们都是好朋友，一半是老朋友，一半是新朋友。好，所以今天跟我们分享的人是 Kevin， 可能会说Constraint solver 的事，然后 Peter 会说Eclipse Tech 的东西，最后 David 会说那个 Firewall 的东西。现在我要分享英文。So that's where I want to go. Let's get started. This is our first speaker is Kevin. Kevin, he designs interfaces for the playful exploration and manipulation of abstract concepts. He's built tools for wind turbine operators, genetic engineers, and manufacturers of hipster housewares. When Kevin is not computering, he enjoys industrial design, Olympic lifting, and snacks. Take it away, Kevin.
All right. Thanks for the introduction, Oscar. So I'm going to be speaking about the synthesis of loop-free programs. And this is papers we love, so there's a paper of the same title. But really, for me, this was actually a blog post that I love. This is how I found out about this paper from this guy, Nick Fitzgerald. Super wonderful, in-depth blog post. And what I like about this paper and this blog post is that it has to do with SMT solvers, or SAT solvers. And this is something that I've been interested in for a while, and what I really like about it is, the way I think about it, it's kind of like having a special genie. And if you can ask the genie a question, oftentimes it can give you an answer. And the main sort of takeaway that I want you to take from my talk is that whether or not you do stuff with SAT solvers or you do stuff with program synthesis, learning about how to separate these two things, to separate how you solve or implement a problem and program it, that's sort of different than how you might specify or talk about or abstractly what your problem is. And if you learn to do those things separately, you can take advantage of some of these things like SAT solvers, but you can also, maybe more pedestrian, it's very useful interacting with other people, or like your employees, right? Like, don't have to get into details of how you might manage stuff. You can say, hey, this is the problem that I want you to solve, and if you get good at expressing that and describing that, you might be pleasantly surprised that someone comes up with a better solution than you would have come up with on your own. So that's the takeaway that I want you to take from this talk. And and like kind of genies, it's sort of, the tricky part is that they will do exactly what you want, right? You've got to be careful how you ask them for things. And in our case, the genie speaks this special language of like existential logic and all this sort of stuff. So that's what we got to figure out how to do. So the talk is in 4 parts. I'm going to talk about the basics of the sort of SAT, SMT solvers, so you're familiar with them. We'll talk about program synthesis, kind of at a high level, more abstract way. We'll talk about component-based program synthesis, which is a specific way to implement this, do this. And then we'll talk about counterexample guided synthesis, which is kind of one weird trick to do this in practice, and how you solve this in practice. Okay, and it's a small crowd, so if you have questions or whatever, feel free to stop me and ask. We can test it. Okay. Solver basic. Actually, how many people here are familiar with SAT solvers or SMT solvers?
Right. Some. I've heard a few times.
Okay.
I heard it last week.
You heard about it last week. Perfect. Okay, so we'll start slow. At a very high level, the solvers, they can help with these sort of logical existential questions like this. So you might say, hey, there exist 2 numbers, x and y, and I have this constraint that x and y added together equals 8. And what you can do is, this is sort of mathematically how you write this. We can see this is how you would write it for, there's one solver out there called Z3 from Microsoft, which is really nice. And this is how you would write it for that system. But kind of looking at it, right, you're like, I'm going to declare these 2 things, x and y, they're integers. I'm going to assert that x plus y equals 8. And then we'll check to see, can we satisfy this problem? And if we can we get a model, which is to say, can we get an assignment of values to these variables that satisfy all the constraints? I guess I'll give you a quick demo here. So if you wanted to do this, the other thing that's really nice about Z3 is like Microsoft put it online. So you can just go here, and then you can sort of type this stuff in, and then when you run the program, it'll say like, yes, I can think of two numbers x and y, right? Like I can think of 0 and 8. That goes together. So that's kind of the idea, right? You ask the Genie gives you an answer. And you can add more constraints. You can say like, hey, let's have x and y, but let's say they're both odd, right? So here, rem here is a remainder. So we're saying, hey, not only do they add up to be 8, but I want them both to be odd numbers. Okay, so you can do that. Anyone think of any models that would satisfy this?
3 and 5.
3 and 5, sure. 7 and 1. There you go. You can say, hey, the other thing that's kind of neat here, you can say, what if we wanted to say one should be odd and one should be even? Right? Yeah. You can't do it. Look at that type. I'm dying. I was telling Oscar, I did this in Keynote, and I had to translate it to PowerPoint so we could get it displayed here. There might be surprises here. But, yeah, so here's the thing. So when the Genie says it's unsatisfiable, it's not saying I couldn't find an answer. It's saying I can prove that there is no such answer. It's very important, because then you can actually do some clever things with that, which we'll see later. Okay, so this is very, I don't know, maybe kind of abstract or sort of boring, right? So dry mathematical stuff. When would you actually use this in practice? I actually had an example where I used this maybe a month ago, and it's because I needed to ship some stuff from America over here. And if you go to the post office website, there are all these weird rules about the packages, about like how long they can be, and like different properties of like the proportion of width to height, stuff like that. And because I'm a computer nerd, I was like, hey, what is this? The ship all costs the same. So I was like, what is the maximal volume that I can ship here, in this package? So this is what it would look like to sort of encode that. It's like, okay, I have length, width, and height, integers. Girth is a sort of, if you wrap a little string around the package, like in this diagram. And yeah, there are these rules. Like the girth plus the length has to be less than 79 inches. The length has to be less than 36 inches. And yeah, dividing two. We want to, here's what the volume is. It's length times width and height. We want to maximize the volume. And so you can ask the Genie this, and the Genie will tell you that you need a length and width of negative infinity, which is kind of, it's like, right? Like this is not the Genie that you want, but it's sort of like what I think is really funny about solvers, because they'll give you an answer, just like a Genie, and then you find out later, like, oh shit, this is not actually what I wanted. I can't find a package that has like negative infinite width, right? And you can see the problem here, once it's been pointed out, you're like, yeah, nowhere in here did I say those numbers need to be positive, right? So then you have to sort of go back and say, like, I need to have length, width, and height greater than 0. Okay, so that's stat solvers. They've been around for a long time. I think in the past 5-10 years, there've been a lot of like implementation advances that make them much more practical for larger problems and stuff like that. So you can start doing interesting things with them, which is what we'll see next.
So what was the ideal length with after you had those constraints?
Oh, I didn't. So yeah, I got that, and then I realized I'm asking my friend in the U.S. to send this to me, and if I asked them to build a custom-sized box, it would be more than our friendship. So I was just like, you should just use a box that you already have. So I think they're shipping that off the shelf. But yeah, those are the sort of problems that you can solve. And it's fun because if you go back and look at it, right, it's not. I hope you can kind of squint and be like, I could see how I would mess around with this for 10 minutes on this website and like get this nice answer. And this is the kind of thing where it's like, it would actually be very hard. I don't really know how to do this in like Python off the shelf or like any other, some other language. It's not obvious how you would optimize this. So that's kind of a neat thing about that. Okay, so those are the basics. How does this apply to program synthesis? And like, what is program synthesis anyway? To talk about that, I'm going to use an example problem, which is the same example they use in the paper, which is a sort of bit manipulation problem. So here's an example of what that is. So what we want to do is we want to find a program that, when given an input which it's like one of the things on the top. We want to take the rightmost bit and then turn it off. So take the rightmost set bit and turn it off. So if you look at the top left, right, right. So this is the rightmost one. This is the output. We want to turn this off. So that's sort of the problem that we want to solve and what they use in their paper as an example. And I don't know how much, have you guys done a lot of the bit manipulation kind of programming stuff? You can imagine ways to do this. And like maybe, at least for me, I'm not super familiar with this domain, but like I would think, okay, here's my input, and I'll start maybe from the right side, and I'll start like looking over and be like, okay, is this bit set? No. Is this bit set? No. Okay, this bit is set, so I should flip it, and that gives them an output, right? Like, this is one way you could solve this.
So can you restate the problem? You're trying to find a map to flip which bit is control.
So what you want to do is find a program that, given some input number, that will be represented binary, you just want to turn the rightmost set bit off.
Oh,
Yeah, so right
yeah.
here. So yeah, that's a problem. So this is how, you can imagine trying to do it this way, sort of looping over and doing it. But, this is not, it's probably not ideal, right? Like you can imagine having, in machine word and a lot of architectures now is like 32 bits or 64 bits, right? So if this one bit is all the way over on the left, you might take 60 odd instructions to like look all the way before you get all the way over to turn it off. And the thing to remember is like in machine hardware now, there's a lot of different instructions in the hardware that operate on the entire number at once, right? So you have things like bitwise not, or you can do shift, and you can do arithmetic. So you might wonder, can, instead of doing this kind of slow looping thing where it's like linear in the size of the input, can you use these existing operations that operate on the entire machine word at once to come up with a program that does this? Okay, so that's the sort of running example in the paper. And if you want to think about it for this talk, I will tell you that you can do it with just 2 instructions. So you chew on that while we're talking about this. Yeah, we try and work it out. But in the meantime, we will ask the genie. And again, remember the genie only speaks in terms of logic, so we got to figure out how we're going to translate this problem into this sort of predicate logic world so the genie can give us an answer. And to frame this problem at a very high level, this is what we're trying to solve. We're trying to say there exists some program P such that for all inputs and outputs, I know, the program running on the input gives you the output, and all of that implies that the specification of our problem is met. And so this specification is sort of where the specific part of your problem comes in. So in our case, what we need to do is say, like, how do we translate our like clear rightmost bit? How do we translate that problem into sort of logical language that we can tell the genie about? Right? Question? No. Okay.
We just if you no. Sorry.
I've gotten you sidetracked, but you're trying to solve the problem, huh?
No, I tried to figure out the spec, but
Okay. Yeah. Well, so what does that spec look like? If you wanted to say clear the rightmost bit and do that with this sort of logical thing, this is what they give in the paper. And I just want to, I'm showing you this to kind of give you a flavor of what this looks like. So here, what we're doing is saying this is just a conjunction. So we're going to say for all indices t from 1 to the size of the machine word, if the input bit at position t is set, and all the indices sort of to the right are 0, then that should imply that in the output, that position is now 0, and everything else is the same. Okay, so this is how you specify this problem kind of in this logical way.
oh, we are counting the bits from the left to right.
We're trying to clear the furthest right bit.
Okay.
And so I guess here, we're counting from left to right.
Oh, I see.
Yeah, I guess that is a little, it's mixing math with the computing stuff. So it's, but, yeah, so this is on paper. And so that's this sort of specification thing. And the next question or problem here is, right, we're saying there exists some program P. And when we saw the Z3 solver stuff earlier, the issue is that the data types that it has, like there is no program P as like a data type that we can ask it to find a solution for. It only has things like integers. Okay, so that brings me to the next part of our talk, which is like component-based synthesis, aka how can you write a computer program by just shuffling a bunch of integers around. And so that's sort of the next part. And the idea here is it's pretty clever, and also I guess it's pretty simple at the same time. So let's see if this makes sense. I'll try and explain it to you. So what you do is you start off with a pile of functions. So here we have F1, 2, and 3, and if you're thinking about writing a program, the first thing you do is like put them in some order, right? You think of like putting them onto lines in your program. So you can put them in 1, 2, 3 like this, or you could just as well put them in like, oh, we'll call function 2 first, then call function 1, then call function 3. So those are the sort of, you can think of this as the lines of the program, so you have a 3-line program with these 3 pieces. At each particular line, those functions will return some output value, and the functions also take arguments, and so you kind of again have choices here. For any given function, you can say like, should this take the input as its argument? Or maybe, on the second one, it could take the input, or it could take the result of the first line as its argument, right? Same thing, maybe function 3 takes 2 arguments, you kind of pick some of the other stuff, and then you just return the last one. So this is a little bit hand-wavy. There's details in the paper, but I want to sort of give you a flavor of what this is like. And so it's just, the way I think of it is like, you just have a set of functions. So it could be like, I have 3 additions and 1 OR, and so I need to just like arrange them kind of just wire them together in some arbitrary way. And so in this program synthesis problem, when you see this sort of, there exists some program P, you can think of it as like, there exists some set of integers that I'm going to use to like map all these components together, kind of order them or whatever. And again, you can look at the paper for more details. Like they go through like, this is, if you have 2 functions, there's like 6 possible permutations. So you can kind of like look at these and be like, oh, here are all the different ways you can do it, and then here are all the sort of integers that say which function is on which line, and like which argument comes from which place, and stuff like that. And so this is kind of the high level idea. There's like constraints where you kind of need to say, a function can only take results from lines earlier, right? It can't get results from lines later, stuff like that. It's all in the paper. 2 things to point out about this. One is like when you sort of generate a program or synthesize a program in this way, you'll use all the pieces that you gave the program synthesis routine, even if those pieces aren't necessary for your solution, right? Like it could be that you gave it like 3 additions, but it managed to like solve your problem with only 1 addition. And if that happens, it ends up just being like dead code in your program, right? So like if here's an example, if it turns out function 3, if you just take the input and give it to function 3, for both arguments, that solves the problem. It still needs to put function 1 and 2 somewhere. That's okay. What you do is you synthesize the program, you get your answer, and then at the end, you run it through standard compiler stuff or whatever, and it's like, hey, this is that code, this is what it is. That's sort of, don't have to worry about it.
And so for our like use case, we can think of these functions as like instructions.
Yeah.
Okay.
Yeah. So in the paper, they talk specifically about bitwise instructions, and so it can be that. And all of each particular piece, you also have to sort of specify logically how it operates. So the other thing that's nice about using these very small functions is you can tell Z3, in logical language, like this is the relationship between this function's inputs and outputs. The other thing is like sometimes you will actually want to have constants. So it could be that in your program you need to and things with the number 17 or whatever. And that's also okay, that fits in this framework. What you do is you just say, you can think of it as like, here's a function that takes no arguments. And what you do is you just essentially quantify over that in the larger solution. So you say, okay, here's some constant, it's going to go in somewhere here. And when you're solving this problem, you say, there exists some program and some constant C. And so it sort of spits it out as well. Okay, so these are all the sort of pieces. So So now it means we can synthesize programs, right? We figure out how to write programs by just guessing around with integers. We figure out how to represent our problem in terms of logic. So we're good, right? Not quite. This program, it turns out that this is a little too hard in practice to do with SAT solvers. This is a little bit beyond my pay grade, but my understanding is basically this sort of there exists for all class of problem is just very hard to solve. And so what we do, and sort of going through the last part of this talk, is this idea of counterexample guided synthesis, which I kind of think of as this one weird trick for turning there exists for all problems into purely first order existential problems. And so it's sort of a way that you can use existing solvers on these kinds of problems. And it's actually it's very neat. It's a pretty clever idea. What you do is you don't worry about for all inputs. You say there exists some program P, and I'm just going to come up with one input-output pair that it's going to work on, right? So you just find that, find one input-output pair, and then you can solve this problem very easily, or you can, right? So it'll come up with a program that satisfies this constraint. And then what you do is you solve another first-order problem. You say, I bet there exists some input and output pair such that this program we just came up with doesn't work. Okay, so you use the solver to come up with an example where the program doesn't work. And then once you have that, you go back to this problem and say, okay, let's find another program that works with both of our examples. So you kind of go around this little loop, and it turns out in practice, for a lot of problems, once you find 4 or 5 counterexamples, when you eventually, you keep going and you find all these specific examples where you want your program to work, and at some point, you will try and run this thing, and the genie will say, this is not satisfiable. And again, what's cool here is that this doesn't mean I can't find an answer, it means I can prove there is no such answer. And so, if you have a program, and you can prove that there is no input and output that doesn't work, you've proven that it works for all inputs and outputs. Right? So that's kind of the trick, and then it lets you sort of do this in practice, where you've effectively solved this problem by sidestepping the hardness of this there exists for all, by doing this loop. So
is that something that you instrument the solver to do, or does it sort of infer it's like a static that you use, and then you still write it for all, and then just figures out this counterexample strategy, or is that something you have to manually specify in how you write this?
Right. So my understanding is you have to do this manually, because every time you go through another pass, you're giving it a different problem to solve, right? Because the first time you're find me a program that meets these criteria, because it doesn't really read into it. It doesn't know all these. So it's just here's this big logical statement, and then you come back later with a bigger one. So you just keep doing that. So yeah. So that's it. It's very neat. I would recommend checking out this paper. I guess there's some demos. One thing I found out, I don't have slides for it, but I found out, I talked to a friend of mine, the author of this paper worked at Microsoft Research, right? And there's actually program synthesis in Excel. So I guess, well, how are we on time? Can I give a quick Excel example? Yeah. So Excel. Where's my little? Any big Excel fans in here? It's a very popular programming language that you should learn. It's very good.
Which language?
Microsoft Excel.
Excel?
Yeah.
Oh, I see.
It's very good. Okay, so it's this amazing feature in Excel, and I like it even more because it uses program synthesis. Okay, so what would be like a this is me. Who else has a name? Okay, so what you can do, so say you want to just get everyone's first name. And I know not everyone has first name, this is not a good thing you wouldn't want to put this production, but say you want to just do this split, you need to synthesize the program to basically take the first thing here, right? this slide, I just made this up, so we'll see if this works. Inside Excel, there is this feature called Flash Fill, where you can give it, here's an input, and then, let's see if it does the right thing here. You can ask it to, yeah. Oh, and it gets, I mean, you can do pretty wild stuff. And then, you can imagine writing this program, especially in Excel, there's some way to concatenate or split the string or whatever. But like, we can try and do a numerical on something. And we can even try the example that we have, let's see if this works. Because it probably doesn't know about.
It doesn't know about binary.
Yeah.
Unless maybe you leading.
We'll see. We will see. And you might have to give it a couple examples. Oh, it feels kind of risky.
It's going to interpret it as a date or something.
Yeah. Yeah, we struck out. The other thing is apparently, I think Google Sheets has this feature now. Google Sheets will actually tell you the formula that it generated.
Oh, wow.
It's kind of nice. You can look at it. But
this doesn't try to extract some sort of
Yeah.
formula. It's just
I mean,
data.
it's synthesizing the program to come up with the stuff in the background,
It's
but it's not showing you.
necessarily valid. So
Yeah, that'd be my guess. You can try it.
Can we add more examples?
I mean, it's a fair shot, right? So we could say.
Can you do with the middle name, and then some people have middle name and other don't have?
Right. Wait. I guess this is the one that we want to synthesize.
Can we use a formula?
Oh, this one's not right. This needs to be 0. Okay, so this is 5 zeros, right? Ooh, see?
Oh.
Yeah. It's not quite the binary. Although I wonder if we could make them all strings. I actually don't know it so very well. Anyway, let's not get too deep into it. But yeah, do I have anything else in here? Yeah. This is what we talked about, solver basics, program synthesis. Very cool idea. You specify your problem and let the computer find the solution for you. Component-based synthesis. I mean, it was kind of abstract when we talked about it, but hopefully kind of enough. You just come with all these pieces, try and put it together. Maybe you play around with that later. And then this counterexample stuff, very nice, weird trick. If you do stat solver SMP stuff, might get you out of a bind. Anyway, that is all I have. Thanks.
Thank you.
Did anyone solve the problem, by the way?
Well, go back to the thing. I was thinking something like subtract 1 and then some sort of mass.
Ooh. Yeah. Do you want to see the answer? No.
Sure.
You're shaking your head like you say.
Yeah,
You just leave it as a cliffhanger for half
Yeah.
hour.
Why not? Yeah, we'll talk about it at the end of the meetup. You got another half hour.
Yeah, okay. It sounds fair.
All right. Cool.